Up to now, what we have done is that we have learned the basics of quantum mechanics, postulates, atoms, molecule, Born-Oppenheimer approximation. We have installed the computational chemistry software package ORCA as well as 3 graphical user interface software, Avogadro, ChemCraft and ChemitaX. And we have learned about Hartree Fock. So, what is the chemistry you get within the single determinant picture? So, in this week's lecture, we are going to go beyond the single determinant picture and we are going to take care of what is missing in the Hartree Fock approximation, and that is called an electron correlation. So, the outline for this week will be like this. So, we will introduce what is electron correlation and what is how it is missing in the Hartree Fock picture. We are going to know about different ways of including electron correlation, many body perturbation theory, configuration interaction, as well as couple cluster, which is considered as the most state of the art among the 3. So, let us start about what is missing in the Hartree Fock. The Hartree Fock method provides a first approximation to a system wave function using a variationally optimized single determinant configuration. It is not accurate as it simplifies the electron-electron interaction by treating them that each electron is moving in an average mean field created by others. So, instead of taking the interaction 1 to 1, it is taken average interaction where each electron is moving in the average field of other electron. That is why it is called also a mean field picture. And the total energy calculated by Hartree Fock will always be higher than the exact energy, as it does not fully capture the electron correlation. At the same time, it is a variational method, so it cannot go below the exact energy. And although Hartree Fock accounts for the exchange effect, the so called Fermi correlation, which prevents electron with same spin from occupying the same space, it fails to describe what is called a Coulomb correlation. This Fermi and Coulomb correlation is a very loose term, but essentially it means that the electrons of opposite spins should also avoid each other, because they are charged particles. For the Coulomb interaction, they are supposed to avoid each other. But in the Hartree Fock picture, the probability of finding 2 electrons with opposite spin in the same orbitals are treated as independent of each other, which does not reflect their true behavior. So, this is the origin of what is called a correlation effect, and Hartree Fock cannot fully describe certain physical and chemical phenomena because of this average mean field picture. So, let us see at this energy picture. So, let us think this is my exact energy, and the Hartree Fock energy, because of its variability, will be somewhere up. Remember, when I say Hartree Fock, I am talking of Hartree Fock calculated within a one particle basis function. So, I have to increase the basis function to go to the exact Hartree Fock method, that is the complete basis set limit. So, that will be somewhere below, and we have shown in the previous weeks videos that if you increase the basis set, your energy lowers down. So, this is how the Hartree Fock limit will be, and once you include the post Hartree Fock method, the energy will further come down. Now, question is that can it go down the exact energy? That is a difficult question to answer actually. It depends upon what kind of post Hartree Fock methods you are using. If you are using a variational method, then there is a guarantee that it cannot go below the exact energy. Whereas, if you solve it like a perturbation or projection, it is very difficult to guarantee that will not go below the exact energy. So, now what is electron correlation? Electron correlation is the thing which is missing in the Hartree Fock picture. As straightforward as that. Whatever is missing in the Hartree Fock is electron correlation. It can be categorized into dynamic and static correlation, or static is sometimes called non-dynamic. We will come into that, what is static and what is dynamic. The correlation energy has a clean definition, and the correlation energy is defined as the difference between the exact energy and the Hartree Fock limit energy. So, E correlation is the exact energy minus this one is Hartree Fock. I could have written as E Hartree Fock. Now, because my E Hartree Fock energy is higher than the exact energy, so the correlation energy will always come with a negative sign. And if I add this correlation energy with the Hartree Fock energy, the energy will go down from the Hartree Fock. Of course, we do not know the exact energy, because we will solving everything in a one electron basis. So, we can sometimes calculate it for a specific one electron basis set, and that is what we are going to use in most of the cases. When we say as correlation energy, we will mean basis set correlation energy. That means that is the difference of the exact energy within that particular one electron basis and the Hartree-Fock energy on that particular basis. So, correlation energy will be synonymous to basis set correlation energy for all this discussion. And post Hartree-Fock methods provide a framework for electron correlation energy by going beyond the mean field approximation. Now, just try to think this one visually. So, there are two axes. One is the hierarchy of n electron model. So, I am starting from Hartree-Fock and treating the electron correlation as accurate as it can. So, I am moving in the x axis, whereas in the case of y axis I am moving in the hierarchy of one electron basis. In principle, I can go to a basis set limit or the infinite basis. So, if I to get to the exact solution of the Schrodinger equation, I need to go high on both the axes, both an x and y at the same time. In that case, I can reach to the exact solution of Schrodinger equation. So, if I am residing within the Schrodinger equation picture, it is a two dimensional plot. One dimensional is the accuracy of the electron model we are using, and the other axis is the basis set limit. If I want to go to a more general picture, in that case there will be a third axis which will contain the Hamiltonian, how you are treating with the Hamiltonian. You can start with a non-relativistic Schrodinger picture, go to scalar relativity, 4 component relativity, cube, and going up to the full quantum electrodynamics. So, this will then it will become a 3 dimensional picture, but for the Schrodinger equation solution it will be a 2 dimensional picture, and to get accurate answers, exact solution to the Schrodinger equation, I need to go up on both the axes. Now, what is static versus dynamic correlation? So, dynamic correlation characterizes the instantaneous interaction among the electrons within the main electronic system. Remember, in the Hartree-Fock, I am considering that each electron is moving in an average field of other electrons. Suppose I have a class full of student. In the Hartree-Fock, what will happen is that each student will face an average interaction by the other student, and if the teacher is present, then maybe of the teacher. Whereas, the instantaneous interaction between the students, chit chat, that is missing in the Hartree-Fock picture. Whereas, this chit chat is actually the dynamic correlation, that the instantaneous interaction between the electrons, and it originates mostly due to the short range Coulombic interaction between the electrons. Because it is a short range interaction, this leads to certain properties for electron correlation method, and that is which we are going to exploit in subsequent lectures. But remember, dynamic correlation is always a short range property, and it can be accurately described using the so called single reference post Hartree-Fock method. That means, for dynamic correlation I can start with a Hartree-Fock picture. Hartree-Fock will give around 95% of the total energy, and rest of them I can recover by doing a correlation treatment on the top of that Hartree-Fock determinant. On the other hand, the static correlation refers to the interaction that are not dynamic or instantaneous. Instead, they depend upon the electronic configuration of the main electron system. So, they arise due to the interaction between the different possible configurations which are possible for the same state, and it originates due to the degeneracy of certain orbital due to their proximity in energy. So, because certain orbitals can have very similar energies, they will have degenerate configurations, and the interaction between them leads to the origination of static correlation, and the static correlation generally cannot be treated by starting with an Hartree-Fock referent. When I make this statement, it is a loose statement in a sense that to treat the static correlation, in principle you need a multi-reference picture where your 0th order reference state contains more than one determinant. Unlike the single reference case where only one determinant is present, and that is the best possible determinant, and in this case you need to go for a multi-reference picture. Complete active space methods or CAS based methods gives you that kind of description. But remember, this static and dynamic correlations are pretty loose term. Practically it is difficult to provide a quantitative separation between these two components of the correlation. Why I say so? Let us say I start with an Hartree-Fock and do a full CI treatment on the top of it. Hartree-Fock is a single reference method, and full CI I can do a single reference CI. So, in that case, using a single reference CI I can still recover all the correlation effect, although they may have static correlation, and even the orbitals are degenerate at the full CI level, I will still get the exact answer. So, it is very difficult to separate static and dynamic correlation. Most of the time you can actually take care of the sum of the static correlation by using higher order correlation methods using dynamic correlation and vice versa. What has a clean definition is the correlation energy, what is missing is the Hartree-Fock is correlation. The separation between static and dynamic is not so straightforward, but then the question is that why I am bothered to know what is static and what is dynamic, because for all practical purposes I will not be able to do a full CI calculation. So, I have to do an approximation. When I need to do the approximation, it is important to know which kind of cases I am trying to treat. If I want to treat dynamic correlation, I will make one kind of approximation. If I want to take static correlation, I need to take the other kind of approximation. So, this insight gained from this concept are crucial for developing model that will satisfactory solution to the Schrodinger equation in an approximate way. Now, post-Hartree-Fock method. So, these post-Hartree-Fock methods are generally sophisticated computational techniques in quantum chemistry that aim to enhance the Hartree-Fock approximation by explicitly accounting for the electron correlation error on the top of Hartree-Fock. So, this post-Hartree-Fock method always start with a reference Hartree-Fock determinant, and generally for Hartree-Fock will recover around 95% of the correlation total energy, and rest of the energy is called correlation energy. These methods yield more accurate representation of the electronic structures and atoms and molecules than what you get in the Hartree-Fock, and because Hartree-Fock method is used as a reference, so one need to make sure that the contribution of the correlation is not very high, because if my energy is very different from my Hartree-Fock, then it may not be captured by an approximate treatment of the correlation. We will see when we will discuss the approximate treatment of perturbation and configuration interaction, and we will know more about it. So, all the post-Hartree-Fock method can be generally classified into two main categories. The first one is perturbative, where molar placed perturbation theory is an example, where you treat the electron correlation as a perturbation from the Hartree-Fock orbital, or you can use a non-perturbative method which uses a variational principle using configuration interaction. So, this is generally more easier. So, configuration interaction is conceptually much more easier than perturbation, but in practice they are more difficult to calculate. And there is a third category of method, there is a which is called coupled cluster theory. This is not variational nor perturbational, and these are typically solved by using projection techniques. So, this is entirely different in philosophy than the molar placed perturbation theory or configuration interaction. So, we are going to look at it one by one and going to know about their relative strength and their weaknesses.